Pues estamos en YouTube. Cuando queráis.
Whenever you want, Bradley.
Pues...
Great. Yeah, okay. Well, it's a great pleasure to have Daniele Gaggero to come and talk to us today. Daniele got his PhD at the University of Pisa in 2011, working on, among other things, cosmic rays and gamma rays. He then went on to do a couple of postdocs. He did a postdoc in Trieste in Italy, followed by a postdoc at the interdisciplinary Grappa Institute in Amsterdam, which is where I had the great pleasure of working alongside Daniele. And he's currently a La Caixa Junior Leader postdoctoral fellow at the IFT in Madrid, where he leads a small group, PhD students, master students. That was since 2018, I think. So he's been there a few years now, developing a group, working on a great many things. In the past, he's worked on cosmic rays, gamma ray searches, and all manner of things dark matter related. One of his main focuses right now is on primordial black holes and how we might be able to detect them in gravitational waves, but also with electromagnetism. And I think that's what he's going to tell us about today. So unless there's anything else, I'm happy to hand the floor over to Daniele. Thank you very much.
Thank you. Thanks, Bradley, for the introduction, and well, thanks for the invitation. So yeah, I will talk about primordial black holes today, in particular about possible avenues toward detection of these objects. So yeah, here's the outline of my talk. I will start with some introductions. I will explain what these objects are, what these hypothetical black holes are, and how the quest is connected to the search for dark matter in the universe. And then I will talk mainly about two different ways to possibly detect primordial black holes. One is centered in our own galaxy and is based on the study of X-ray and radio data. And the other one is looking at cosmological distances and is basically based on studies of the gravitational wave emission from black hole mergers. So yeah, let me start talking a little bit about black holes. In particular, let me start about talking about the black holes that we know about, that we're sure that are around. So first of all, we know that there are stellar mass black holes that are supposed to be the end point of stellar evolution, and they're basically typically detected when they accrete matter from a companion star. And these systems made of a star and the accreting black hole are called X-ray binaries. And you can see here a couple of nice pictures about them. And then we know that there are supermassive black holes, typically at centers of galaxies. And these are observed up to very, very large distances. And these are all the black holes that we have been studied for a long time. Very recently, we are studying stellar mass black holes that are a bit heavier than the ones that are part of X-ray binary systems, and we can detect them when they merge, and by observing the gravitational wave emission associated to the merger with the interferometers like LIGO and Virgo. And you can see in this nice plot that all these systems that merge have a little bit a larger mass compared to the mass of the black holes that are part of the X-ray binary system. So they form a more distant and a slightly more massive population. And there are many events like this that are we have been studying for several years. Yeah, but then there is the hypothesis that other types of black holes exist in the universe. We call them primordial black holes because they would have formed not at the end of the stellar evolution, but in the very early universe, so in the very actually the very first second after the Big Bang, a fraction of a second after the Big Bang, in the so-called radiation-dominated era. And their existence has been proposed in the early 70s by Stephen Hawking. And these black holes are very different from the astrophysical ones. Also, they could cover a very wide mass range, and they could be as light as they could form with the mass as light as the Planck mass, and they could span masses up to thousands of solar masses or even more. And yeah, just a little bit of technical slide. So the mass of actually of a primordial black hole is supposed to be the mass of the associated to the horizon at the time of formation, and these objects should form when a overdensity that is produced somehow in the very first phase of the history of the universe, the so-called inflationary phase, re-enters the horizon, the moving Hubble horizon, and eventually collapses and form a black hole. So in the very early universe, there is the possibility, given the peculiar environment of the early universe, in particular the extremely high density, to have a overdensity of order 1, if present, to collapse and to form it's called a primordial black hole. And yeah, this connects to the dark matter problem. So this idea has a nice connection with a mystery of modern cosmology and modern astronomy, that is the dark matter problem. So we know that there is missing matter in the universe. There is matter in unknown form that doesn't emit any electromagnetic radiation. And we have evidence for the existence of this form of matter at many different scales. So, for example, we have evidence we see here the galactic scale, which was studied extensively, for example, in the 70s by Vera Rubin and other scientists. And here we have evidence for the presence of missing matter, because the velocity of the sun and stars in our galaxy is much larger than the one that is expected by assuming that there is only matter that emits radiation. But then the most striking evidence is a cosmological scale, and actually we know from the study of the cosmic microwave background and from the study of structure formation at very large scale in the universe, so clusters of galaxies and such structures, we know that cosmology requires the presence of a significant large amount of missing matter that we call dark matter. And yeah, primordial black holes are a dark matter candidate. Actually, in particular, if a primordial black hole is more massive than order of 10 to 16 grams, it would be stable over the Hubble time scale, over the history of the universe. Well, if it's lighter than this, it would evaporate due to the emission of Hawking radiation. But if it's more massive than that, it is stable, and it is an excellent dark matter candidate, as stated actually already in the very first paper in 71 by Hawking, who wrote that it is actually tempting to suppose that a major part of the mass of the universe is actually in the form of collapsed objects like primordial black holes. So yeah, that's what we are studying. And this is the hypothesis we are studying in this period, among others, of course, because there are many other possibilities for the dark matter. It could be a new type of particle, of course. That's another widely studied possibility. And typically, yeah, what we study when we look for a primordial black hole is can be visualized in a plot like this. So we typically study in different ranges of masses what is the maximum allowed density of primordial black holes in terms of the total dark matter density. So we, as usually in dark matter studies, we place upper limits on the abundance of a dark matter candidate. In this case, on the abundance of primordial black holes. And this is a field that is evolving very, very rapidly. And there are many ways actually to either constrain the abundance of primordial black holes or, of course, detect possibly a population in the future. Yeah, you can see that, for example, there is a window that is quite open at the moment. There's been a lot of debate and development in this region, but it is still possible that black holes that are primordial black holes of very small mass, like 10 to the minus 15, 10 to the minus, around 10 to the minus 15 of the mass of the sun could be almost all of the dark matter, all of the dark matter. Then there is there is a very broad mass range where you can study the problem, you can look for these objects by studying microlensing events. So this means that you basically monitor a large number of stars and you look for magnifications of the light curve of those stars due to the presence of a black hole passing by along your line of sight. And this is a very, very promising way to either constrain the abundance of primordial black hole or to detect a population. Historically, it was very important. So the EROS collaboration, for example, and the Macho collaboration reported very famous upper limits. And also there are some hints, so this is nice. For example, this experiment reported some microlensing events that could possibly be associated to a population of planet mass primordial black holes that could amount to some fraction of the dark matter. But of course, it could be there could be another explanation, for example, like unbounded Earth-like planets. Or so these are small hints that are not so significant yet, but are still interesting. This means that this channel of microlensing, of monitoring the light curve of stars in a given region is promising and is very, very sensitive. But yeah, actually today I would like to talk about this mass range, the masses that are a bit larger, like between the mass of the sun, one solar mass, and tens or even hundreds of solar masses. And this is a very crowded region in this plot. So there are a lot of things are actually going on, and there are a lot of ways to possibly detect primordial black holes in this range of masses, so between solar mass and tens or hundreds of solar masses. And this, again, has developed very quickly in the latest years. So actually this mass range was under the spotlight because there was actually a debate about the gravitational wave events detected by LIGO and Virgo. So LIGO and Virgo detected, as I said, a gravitational wave emission from a number of black hole mergers. So actually detected black holes, massive black holes with masses that span a large range from 20 to almost 100 of solar masses. And there was a debate whether these black holes were actually primordial. So if or at least a part of this population that was detected by LIGO Virgo was primordial. And then there was a discussion about some constraints on this hypothesis, and that's basically the topic of today's talk. So two different ways, again, to either place upper limits, bounds, as we say, on the abundance of these objects in this particular mass range by means of X-ray radio emission searches or merger rate estimates. I will explain what is it about, of course. But let me emphasize that the typical question is, okay, one, can we set an upper limit on the abundance of primordial black holes? Two, can future experiments either set a more stringent upper limit or detect a subdominant population? So it's still extremely interesting if primordial black holes in this mass range don't make up all the dark matter, but make a subdominant fraction of the dark matter, even 1% or per mil or even less of the dark matter. Because as I will show, this has consequences for many things, for fundamental physics. This means that these objects could form, that this means that there is some mechanism, possibly during inflation, that forms these objects. This means that these objects could actually be the seeds, for example, for supermassive black holes. And this has consequence of our knowledge of about the nature of dark matter in general, as I will show in a moment. For example, if we show that these objects exist even in a subdominant population, we can exclude, for example, some popular dark matter candidates that can't live together with a subdominant population of primordial black holes. And then, another question that we always ask is whether these bounds can be evaded by some specific models. So that's the question that always arises. One can imagine peculiar mass functions with complex structure, and the question is whether these mass functions can evade these upper limits, which typically rely on the assumption that at each given mass, you have a monochromatic population of primordial black holes, or possibly log normal population, but still simple mass functions. So the question is whether complicated mass function can exist. So there are a lot of questions associated to these searches. And yeah, let me just flash in a bit more detail what I mentioned before. So that's interesting. So if we were to detect even a very small fraction of dark matter in the form of primordial black holes, this has consequences on our knowledge of the bulk of the dark matter. So, for example, if dark matter was constituted of WIMPs, of weakly interacting massive particles, which is a very popular dark matter candidate, then these particles would cluster around these primordial black holes, this subdominant population of primordial black holes. And given that WIMPs typically annihilate into standard model particles and produce significant yields in gamma rays, this would produce a large number, this would imply the presence of a large number of gamma ray sources in the sky, both point sources and diffuse emission, integrated diffuse emission. And by comparison with actual data, one could, in principle, set extremely stringent bounds on the annihilation cross-section of the WIMPs. So the logic is, if we were to detect even a very small fraction of dark matter in the form of primordial black holes, we could exclude basically most of the parameter space associated to the hypothesis of the existence of weakly interacting massive particles. It is a very popular dark matter candidate, and realizations of this candidate exist in many extensions of the standard model of particle physics. So we could exclude the presence of this, basically of this class of particles as main contributors to the dark matter. But yeah, this was to give the idea of how important it is to look for primordial black holes in general, and even to look for a very small fraction of the dark matter in the form of primordial black holes. Yeah, so let's go to the first part. So how to look for these objects? So one way is to look for the radiation that is emitted by matter, by ordinary, as we say in cosmology, baryonic matter, that is accreted onto them. So the idea is that we are in the galaxy. We consider our own galaxy. We know that there is a lot of interstellar gas in our galaxy. We know that black holes can attract this baryonic matter, and that accretion of matter onto a black hole is an extremely efficient process that that creates heat and radiation with an efficiency that is way larger, for example, than the efficiency of a nuclear reaction. So it's a very efficient process. Matter can enter the sphere of influence of the black hole. The rarefied interstellar gas can be attracted and enter the sphere of influence of the black hole, and can be heated up and actually to very high temperatures, and emit a multi-wavelength spectrum of radiation spanning from radio waves to all the way up to X-rays, to even hard X-rays in the in the 10 to 40, let's say, keV energy range, due to a variety of non-thermal processes that are supposed to happen quite close to the Schwarzschild radius of the black hole, actually in the inner part of the accretion disk that is expected to form around the black hole. So basically, we are looking for this phenomenon that you see you see an artist impression on the left in these regions that you see pictured on the right side. So the regions full of gas, and there are many regions in the galaxy that are that contain a lot of interstellar gas, in particular in the form of massive clouds of typically molecular hydrogen. That's the most important constituent of these clouds. And the region around the galactic center is very promising for this, because there is a very large complex of molecular clouds near the galactic center, and in a region that spans like a few hundred parsec, like a couple of hundred parsec from the galactic center. This is a region that is called the central molecular zone. It's very well studied in different wavelengths, and it's a very nice target for this kind of search. So in order to study this problem, we need to know a little bit about accretion physics. So how this accretion works. And the starting point is this very simple textbook approach, I would say, that is basically based on fluid mechanics, on simple fluid mechanics, so continuity equation, Euler equation. And the main formula here that you get is the so-called Bondi-Hoyle-Littleton formula, which gives an accretion rate, that is the quantity we are interested in, m dot, BHL, that scales as a square of the mass of the black hole. So more massive black holes accrete more efficiently, and with the inverse of the third power of the black hole speed. So fast black holes accrete less efficiently compared to very slow black holes. Yeah, this is a sort of starting point, a very simple approach to accretion physics, but there is more. Actually, the problem is more complicated, because when matter is accreted onto the black hole, you have feedback. You have what is called radiative feedback. So the matter that is heated up emit ionizing photons, emit ionizing radiation that ionizes the surrounding medium. And typically, this problem can be studied by numerical simulations based on solving numerically the equations of fluid mechanics in presence of feedback. And you can see that a ionized region, which is sort of cometary shaped, is typically formed around the black hole. And this changes completely the phenomenology and changes completely the accretion rate. Actually, it turns out that due to the formation of this underdense ionized region around the black hole, at very low, especially at low speed, when at speeds that are slightly supersonic, but not too much, you suppress the accretion rate with respect to the Bondi prescription. And actually, you also change the behavior. So as you can see in this plot, for speeds that are not too high, not too supersonic, you have an accretion rate that actually increases with speed, and you actually have a peak of accretion rate at some given speed. Yeah, so actually you can see from this plot the comparison between the models based on these numerical simulations that we call Park-Ricotti models, because there is a series of papers by these two authors that analyze this problem in detail. And you can see the comparison between the accretion rate based on this Park-Ricotti model with respect to the accretion rate computed with the simple Bondi-Hoyle-Littleton formalism. So that's more or less something about accretion physics that is needed in this study. And so let me now explain the logic. So how we do this kind of studies. So we typically look at this data. So data related to radio emission and X-ray emission near the galactic center. So we have catalogs of sources in, for example, in the gigahertz band from VLA, the Very Large Array radio telescope, and the space mission NuSTAR, for example, which monitored the X-ray sky and produced a survey in the hard X-ray range. So we have this data, and what we typically do is we simulate how many sources would there be in these energy bands if primordial black holes were to form all the dark matter. So we produce sort of Monte Carlo simulations of, we populate the inner galaxy with primordial black holes. We produce simulated maps of the expected radio and X-ray sources possibly associated to these accreting primordial black holes, given our recipe for the accretion physics and given our knowledge of the distribution of the interstellar gas. And what we find is that there are typically way more sources than we would predict many more sources than actually measured. And so we place upper limits. And there is a series of papers in which we place the upper limits first, based on the Bondi-like parameterization, and then, which is the most interesting one here, based on the Park-Ricotti model. And as you can see, it turns out that no more than a per mil of the dark matter seems to be, according to this hypothesis, in the form of primordial black holes. But there are questions. So actually, what happens at lower energy? where is there a threshold? So how can we extend this bound to low mass? Is this compatible with a more complex mass function with several peaks at different masses? Can future experiment improve these bounds? Are we touching also some astrophysical floor? So what if what about astrophysical black holes? Are we reaching the level where we have the possibility to detect astrophysical black holes? So these are some of the questions that we are currently working on, actually, within my group. And let me flash some recent results about this. So this is a work recently done by my student, Francesca Scarcella, and other collaborators. So here we studied actually the possibility to look not only for primordial black holes, but look for astrophysical black holes for our so-called astrophysical floor. And actually, yes, the answer is that there is the possibility to detect a big part of this astrophysical black holes. And the answer is that yes, we are touching the level where even astrophysical black holes are detectable. And probably this plot shows the result in a clear way. So this is the number of expected X-ray sources associated to astrophysical black holes compared to the number of sources detected by new star, and as a function of the average speed of black holes in this region. So you have a lot of parameters in the problem, but so we actually did a systematic study of the parameters of the problem. But the bottom line is that, yes, I mean, the astrophysical black holes are within reach of these searches, and actually already a portion of the sources already detected by new star could be accreting black holes. Actually, they could be astrophysical black holes, they could be primordial, and the question is for the future is how to disentangle populations of these objects. And this is also a science case for future experiments in the radio, for example. So in the radio, there will be a huge improvement in sensitivity with future experiments, in particular the square kilometer array, the SKA. And we found that depending again on the parameters of the problem, thousands of astrophysical black holes, and possibly, of course, also primordial black holes, if they are a subdominant population, could be detected with radio searches, with future radio searches. Yeah, just to conclude this part before moving to the last quarter of an hour, where we'll talk about a different topic. Let me also flash that this is something we are studying in detail now, that there is a possibility to have primordial black holes distributed with a broad mass function, actually with a structure, with multiple peaks that should be associated to events in the early universe. So primordial black holes at these masses should be associated to like pressure drops in the early universe plasma due to different events that change the equation of state in the primordial plasma. And the most relevant one is the QCD phase transition that is expected to occur in correspondence with this peak around 1 solar mass. And the question is whether this upper limit is compatible with this mass function. And naively, well, since actually this kind of search is not so effective around 1 solar mass, because the accretion rate, as you remember, scales with m squared. So there's not so much accretion for black holes that are around 1 solar mass. So there is actually sort of threshold effect. So it's tempting to believe that a peak at very low masses could be partially compatible with the bound. And in fact, from these very preliminary results, it seems that this upper limit is relaxed for this peculiar multi-peaked mass function. Okay, this is associated to a specific model, and this is interesting because this means that at least for this kind of search, but possibly this would extend to other bounds, this peculiar mass function could still amount to a very big fraction of the dark matter or even all the dark matter. So this is something worth studying a bit more in the future. And this is something we are working on right now in my group. But yeah, so that was actually all for the first part. And I think I have possibly, maybe a quarter of an hour to flash another nice avenue toward detection. And yeah, this avenue toward detection is based on the search for mergers. So gravitational wave emitted from black hole mergers, but at very large distances, actually, as we say in cosmology, very large redshifts. And there is a specific period in the history of the universe that is called the cosmic dark age, that is very interesting from this point of view. This epoch started roughly 400,000 years after Big Bang, at redshift roughly 1,000, when the universe became basically neutral, right? When and transparent, and when the radiation decoupled from matter, and this was also before the period where the first stars formed. So the universe was very homogeneous, very well, structures were starting to form, but the universe was mainly made of neutral hydrogen, and there was no ionization whatsoever. There were no stars, and there were no astrophysical black holes because there were no stars. So any merger event associated to this very remote period would be possibly primordial. So that's a target for a search for primordial black holes. So in order to study these periods, we want to study the merger rate of primordial black holes in this epoch, and actually to do this we need a tool, we need a way to compute the merger rate of primordial black holes, and this is what I will try and describe very, very quickly. So basically, there is a merger rate because primordial black holes are supposed to form binary system. At least part of them should end up in binary systems, and this could form very early on in the history of the universe. So if two primordial black holes, a pair of primordial black holes can decouple from the expansion of the universe and form a binary system, which can possibly later merge because it would lose energy because of the emission of gravitational waves. So you have this history here as a function of redshift of a pair of primordial black holes that is first separated by the expansion of the universe. But if the gravitational pull overcomes this so-called Hubble flow, it can form a binary system and slowly in spiral and finally merge and be detected. So we want to study the rate associated to this phenomenon, and we want to study this in a general way. So even in the presence of other forms of dark matter. So this is a work that actually we did in Grappa with Bradley, and we showed that the presence of other forms of dark matter is actually very important because it would exert dynamical friction on the pair, on the binary system, and this is expected to change completely the properties of the binary system. So actually the presence of the bulk of the dark matter due to the many two-body interactions between the black hole system and the possibly particles that comprise the dark matter halo are expected to change the properties of the binary system. So you would look, you would have something like this. You would have two dressed primordial black holes with a dark matter halo around that after the first encounter change their orbital parameters and eventually form a more compact and more circular binary due to the effect of dynamical friction. So what we did is compute this process, and I will skip the details, but I will show the result. So basically we computed the merger rate associated to primordial black hole binary systems in presence of the rest of the dark matter if they are subdominant. And we did this as a function, as usual, of this FPBH, so the amount of dark matter that is in the form of primordial black holes. So again, we found that if primordial black holes were all the dark matter, okay, before we showed that this would create many more X-ray and radio sources. Here we showed that this would create many more merger events. So if primordial black holes were all the dark matter in the universe, the merger rate associated to primordial binaries, so to binaries formed in the very early universe and made of primordial black holes, would be way larger by even 2 orders of magnitude or more with respect to the merger rate measured by LIGO and Virgo. And this is a statement about, well, low redshift, about the period that is, and about the range of distances and look back time that is actually associated to the measurements of LIGO and Virgo. So here we are talking about low redshift, about distances and time that do not arrive at these cosmic dark ages that I was mentioning. But this is the starting point. This is the starting point of our computation, because if you fix a machinery, a tool to compute the merger rate of primordial black holes, then you can extend it to high redshifts. So here the piece of information is that the merger rate can actually be used to compare with, so the computation of the merger rate from primordial black holes can be actually used to compare to the actual data, and again set an upper limit, because the idea is that if primordial black holes were all the dark matter, they would the merger rate would overshoot the data by even 2 orders of magnitude or even more. And actually this is what we did, and taking into account this formalism, we set up, we actually computed again an upper limit on the abundance of dark matter in the forms of primordial black hole, given the data of LIGO Virgo about the merger rate, and given their estimate of the merger rate at low redshift, in the redshift range roughly from 0 to 1, almost 1. That is the one covered by this data. And this upper limit, as you can see, is again very strong. So given all the hypotheses of this calculation, given again also the hypothesis that at each given mass you have basically monochromatic mass function of primordial black holes, this upper limit is at the level of per mil of the total amount of the dark matter. So we don't allow more than a per mil of the dark matter in the form of primordial black holes. But again, let me mention all the caveats about this upper limit. And it is always interesting to check whether there are specific models, for example, characterized by peculiar mass function, that may possibly evade this bound. So in this case, to my knowledge, I mean, this has not been studied too much, but this is always something to keep on the back of the mind when one talks about all kinds of upper limits. And it's always interesting to find models to challenge these upper limits with specific models that evade the bounds. But still, so taking this bound at face value, again, we are still allowed to have a subdominant population of black holes, of primordial black holes. And what I want to flash in the last minutes is that it is very nice to extend the problem at very large redshifts, so very large distances and very large look back time. And the reason is that we expect a completely different trend. So if we were to observe merger events at very large distances, very large redshift, very large look back time, we are expected to see a very different trends for astrophysical and for primordial black holes. So the primordial rate, the rate associated to hypothetical primordial binaries, is expected to increase monotonically with redshift. And this is basically due to the properties of the distribution function of the orbital parameters of primordial black hole binaries, that is peaked toward low numbers of semi-major axes and very high eccentricity. On the other hand, the astrophysical black holes are expected to trade, the merger rate associated to astrophysical black holes is expected to trace the history of star formation in the universe. And there is some consensus that from redshift 2 up to very large values of the redshifts, this value should steadily decrease. And in particular, again, if you get to the to the cosmic dark ages, to the period where the first stars had not formed yet, you expect to have basically a zero rate from astrophysical black holes, because astrophysical black holes again are the end point of stellar evolution. So before the first stars, you have no astrophysical black hole merger rate. On the other hand, you're expected to have a very large rate of events associated to primordial black holes. And this is a window, a very interesting window that can be explored in the future. So it's not possible to test this now, because LIGO and Virgo right now can't reach these very large distances. But future telescopes, like the upcoming Einstein telescope, which has been proposed and has a very interesting science case for many different types of physics. So in this case, the Einstein telescope can get to these very high distances and can probe the merger rate of black holes during the dark ages. So it can see actually in excess with respect to the very small background, and possibly detect a population of primordial black holes. So again, this is something that I'm studying right now with my group, with both master students and Francesca, my PhD student. So we are trying to look at which optimal, we are trying to look in different ranges of redshift and assess whether in some given redshift bin, as a function of the fraction of dark matter in primordial black holes, one can hope to see a significant excess with respect to the, what we call again, astrophysical background. So with respect to the merger rate that you would expect to associate with astrophysical black holes. And this requires, of course, to study also the astrophysical uncertainty. So to study different models for the evolution of the astrophysical merger rate as a function of cosmic time. And typically this is done by bracketing the uncertainty and studying different models for the evolution of astrophysical black hole merger rate. You see this WWP and WWP plus GRB, these weird names. Basically, there are different ways to predict what is the merger rate of astrophysical black holes, but they are basically all based on on tracers. So we assume that the merger rate is linked to the history of star formation over the history of the universe, and this is typically traced by different kind of tracers, by number count of luminous galaxies on some wavelength, for example, or on energetic events like the gamma ray bursts, the GRB. So there are different tracers that can be used to trace the star formation history in the galaxies of the universe, and this implies some astrophysical uncertainty. But still, the key message is that we would like to observe an excess at some very high redshift with respect to this astrophysical background, possibly with future telescopes like Einstein telescope. So yeah, I think it's that was all. So my conclusion is that primordial black holes may exist. They may constitute a significant part of the dark matter in the universe. And very recently, there was a nice debate about how to possibly detect these objects by looking at the radio and X-ray emission emitted by the baryonic matter that is expected to be accreted onto them in the galactic environment. And on the other hand, there is this promising avenue, which is the study of the merger rate at very high redshift with future interferometers like the Einstein telescope. So this is a nice science case for multi-messenger astronomy in the future, for SKA and all these instruments that look for radiation at different wavelengths and from different messengers. And again, it's very interesting even to detect a very subdominant population of these objects, because this would have really, really profound consequences for fundamental physics in general, as I tried to convince you. And yeah, so that was all. Thank you. Thank you very much.
Thank you very much, Daniele. Thank you, Bradley. I think he already left because he had another appointment. For introducing him. This was a very nice talk on primordial black holes. And you were right on time, 45 minutes, Daniele. We are not, this is not Switzerland, we are not that strict, but thank you anyway. So now I open the gate for questions. You can either open the mic or raise your hand and we'll let you know. Chema is raising the hand. Chema, can you talk?
Yeah, can you hear me?
Yeah, we can hear you well. Go ahead.
Well, thanks, Daniele. That was really, really interesting. Very nice talk. So I have a couple of questions. I'll just make one, and if nobody has more, I keep asking. Regarding the center of our galaxy, you were talking about this upper limit you guys set on the abundance of primordial black holes based on the lack of signal that you observe from the data. But I would like to get more clarity on, you were talking about the astrophysical floor, I think you call it that way. And how well do we know how the accretion rate of black holes near the central gigantic one may be based on all the unknowns we may have about the distribution of baryons available to form this accretion disk, and if there is any comparison study that compares possible accretion disk in the center of the galaxy, not the supermassive one, but just regular stellar black holes, with accretion disk in our neighborhood, which are probably easier to study. If there is a difference between them, and how could you estimate that astrophysical floor near the center of the galaxy?
Yes, yeah, thank you. Yeah, that's a very important question, actually. So yes, first of all, let me define a little bit more this astrophysical floor. So maybe it was not so clear on that. So what I'm saying is that the astrophysical floor is the population of astrophysical black holes that are supposed to be like 10 to the 8 in our galaxy. So this would be, this could amount to a per mil. I mean, this would be right here in this plot, right? Because maybe a little bit less, between 10 to the minus 3 and 10 to the minus 4 of the dark matter, right? Because the total mass of the Milky Way is order of 10 to the 12 solar masses. So you may have a mass of from 10 to the 8 to 10 to the 9 in astrophysical black holes. So here, the astrophysical floor, maybe when the study is completed, I can also put a line here at some point. I mean, it would stay at the level of the bound, basically. So you expect to have already 10 to the minus, between 10 to the minus 3 and 10 to the minus 4 of the dark matter, of the matter content in the galaxy in the form of astrophysical black holes. And so we expect to have a population of astrophysical black holes everywhere in the disk of the galaxy, and in particular in this region. And yes, we also expect to have a supermassive black hole at the very center. This is well studied, associated to the Sagittarius A star source. But this is quiescent. So this is now very inefficient in terms of accretion. There was probably a previous history of more efficient accretion, but right now this is actually considered one of the most inefficient accretors in our galaxy. So it's given, despite its mass, the merger rate is very low, and actually. Also the luminosity is very low, so it's very radiatively inefficient. So actually there are two pieces of the problem. One is the accretion rate, and one is the efficiency in terms of transforming this accretion rate into X-ray flux, for example. And we know that Sagittarius A star is very inefficient accretor. So actually we were very conservative when we set these upper limits. So we assumed that, for example, in terms of this luminosity efficiency, we basically picked the most conservative recipe that is actually tuned on both the massive black hole at the very center and the most inefficient X-ray binaries. So I would say that this bound is very conservative in this sense. So we assumed a relation between the accretion rate and the X-ray luminosity that is actually very inefficient and compatible with the inefficient X-ray binaries that we observe. And yes, the central black hole is there, but again, it is in a quiescent state. So this doesn't enter too much our bound, right? So what we are doing is really comparing the number of sources that would be associated with black holes crossing all these clouds that you see here, for example, that are tens of parsec away from the center. So they are not, or even 100 parsec away from the center. So these clouds are there. They're not particularly affected by the presence of this quiescent black hole at the very center. So yes, here you have a region very well mapped in very different wavelengths of like 1 degree more or less around the galactic center. This covers a bit more than 100 parsec. There are many clouds, and we know they are measured. We see the emission from these clouds. We can also measure the mass in molecular hydrogen, because we see for example, the emission from the CO molecule in the millimeter, so we can trace where the molecular hydrogen is, and we know that these clouds are there despite the presence of the black hole at the center. Does this answer the question, or maybe I missed?
More or less. I don't think I put the question in a clear possible way, but I think I got the answer. Yes. Thanks.
Thanks.
I don't see other people raising the hand. So Chema, if you want a second round, be our guest.
I mean, I don't want to take all the time. I think if somebody else has a question, should take the opportunity. But if there is time, I have more questions.
There is time. So go ahead.
All right. So regarding the second part of your talk, the possible constraints based on the LIGO observed rate, I assume that in these calculations you adopted some kind of Gaussian initial conditions for the distribution of primordial black holes, and there's no clustering. And if you allow for some clustering, could you form, or could you increase the rate of merger, a higher redshift, and have a lower rate, a lower redshift that would allow for a larger fraction of primordial black holes given the LIGO constraints?
Oh yes, absolutely. Actually, that's what we are studying right now. So we are trying to assess. So this is really, I don't have a plot at the moment, but this is what we are studying right now. So this curve of how the merger rate would evolve as a function of redshift could be tilted by the fact that some clustering can arise. Actually, when structures form, you expect to form progressively larger clusters of primordial black holes. This problem is starting to be studied also with simulations. So it's not easy, but still there are already both simulations and prescriptions to study this clustering. And actually what happens is that if a binary happens to fall in a cluster of black hole, it would be perturbed quite a lot. And actually it would be basically removed from in many cases. I mean, in a range of sides of the halos of the cluster, they would be removed from the computation, I would say, because basically a little bit of torque exerted on the binary would already increase the merger time, because a slight change of the angular momentum leads to an increase of the merger time with the 7th power. You see the merger time scales with the 4th power of the same major axis and the 7th power of the relative angular momentum of the dimensionless relative angular momentum. So basically, yes, the presence of clusters would change this picture, and possibly, as you said, in the sense of in the sense of removing binaries from the computation and tilting this curve. So you can possibly allow more dark matter in the forms of primordial black holes today, but then you would expect a steeper increase, but this is something we are studying right now. So there are some prescriptions in the literature for how to take into account the clustering. Actually, these prescriptions are for the clustering that is expected to arise as a consequence of structure formation. But yes, I mean, at the moment there is no computation on this, but that's what we are doing right now. Does this go in the direction that you are thinking? So what is your
Yeah, no, that's exactly. Thank you.
Yeah. Actually, there are only qualitative discussions about this, but it's very nice to see how this curve would change. So in general, it's time, I think, to go to more realistic scenarios with, mass functions clustering and study a little bit more these problems, because that's very complex phenomenology.
Well, I don't see additional people asking. Thank you, Gemma, for your.
I still have one more comment, if I may.
If it is short and precise.
Sure, this was actually raised to me a couple of weeks ago by Celso about this new quasar, Redshift 7.6, I believe, with a constraint on the mass of the central black hole, supermassive black hole, of more than 10 to the 9 solar masses. And that is extremely difficult to explain with simple astrophysical arguments. And I was wondering if you guys were thinking about these kind of observations as a way to constrain. This is not a constraint. This actually would be more easily explained if you have seeds of black holes that can explain these gigantic black holes less than 700 million years after the Big Bang. It's a very short time to form these guys.
Oh yes, so yes, no, this is actually, well, I don't have a quantitative argument for that, but yes, that is one of the arguments in favor of the presence of a population of primordial black holes, because exactly, it's very hard to explain the presence of supermassive black holes at very high redshift. Redshift even 7 or even more, and the masses are really high, like billions of solar masses. So I mean, it's very hard. You need some massive seeds, and you need a lot of accretion. It's very challenging to explain. So yes, primordial black holes could help in that. So that's actually, I think, one of the commonly used arguments, right, in favor of the existence of at least some at least a subdominant population of primordial black holes, precisely to explain the existence of these objects that, by the way, they are, I think, 10 to the minus 5 of the dark matter. I mean, supermassive black holes constitute some portion, basically, if you want, of dark matter. And yes, so actually there is the hypothesis that a whole spectrum of black holes, right, exists in between, or even intermediate mass black holes, and from 100 to thousands of solar masses. And basically, LIGO has already seen the first intermediate mass black hole, if you want. So yes, I mean, this is the picture is probably a population of black holes from intermediate mass to supermassive, and the existence of primordial black holes in this mass range could help definitely to explain their existence. Yes, I agree.
Is that good, Gemma?
Yes, thanks.
Thanks to you for giving this some lively discussion here. Well, Daniele, as I said before, thank you very much for this talk and this discussion. Again, the timing is perfect, 1 p.m.
Oh, wow.
Thank you also everybody for connecting today. We had up to roughly 25 people connected, which is great. And thank you, Rebecca and Marta, for organizing this event. So see you next month in the next Las Mañanas IFCA. Bye.
Thank you. Goodbye.